really feel about the same as I did one day. So this is just reviewing here, because I know that this topic kind of throws people. I'll tell you that in chapter 7, by this, I mean, at the end of the chapter, there's this section called exercises. Since I don't have any of these on D2L yet, you want to practice some of these on your own. I'll do some of these, but the ones you want to look at are 61, 62, 566, 67 is, and I'll do some of these now. You get the answers to the even ones in the book, so I'm going to do some of the odd ones. It's 62. Okay. Yeah, 62 is what I wanted. All right, well, let me just do 62. This one. So the reaction given, PI, I did one of these the other day, I'm pretty sure. Do another one. For these types of questions, sometimes you're just asked for the limiting reactant. Actually, usually sometimes you're just asked for the theoretical yield. But to get the theoretical yield, you've got to find the limiting reactant first. So these are all really kind of in order. And then some of these questions have you finish off with the actual yield and the percent yield. And the actual yield is usually what's given. So if it gives you an actual yield, you just have to recognize it for what it is. But of course, the long walk is finding the theoretical yield. You go through kind of a long walk to find the limiting reactant, and then you got to go through kind of a long walk to get the theoretical yield. Starting with B for this one, you're told you have 2.4 grams of titanium, 6 grams of F2. Because grams was mentioned, you're going to need the grams per mole for these. I'm going to have to bring up one periodic table. I don't have one printed out. Titanium is 47.88. Grams per mole. The F2, 19.00 times 2. So that's going to be T times 19 is 38. So you're going to need those things for this. Okay. So grams is mentioned for both of these, so you need the grams per mole for both of these. TI you can get straight off the periodic table. F2 is just 2 times what you see on the periodic table for fluorine. Okay. So in order of things to do, the first thing, you've got to find the limiting reactant. One of those is the limiting reactant. Do you remember what you do here? How you get started?
You pick one.
You pick one. Exactly correct. Pick whichever one you want. I usually just pick the first one. And you start with this 2.4 grams of TI. That means you need grams of TI on the bottom. So we're going to use this 47.88 grams. 1 mole of TI. Next, you need moles of TI on the bottom. This term that I'm putting together right here is this one. 1 mole of TI to 2. That's the molar relationship of the reactants.
Is this supposed to be 47.88?
Yes. Thank you. You guys always call me out when I make a mistake. I'm never going to deny it and pretend I didn't. So you need the grams per mole for this thing, which is this. You need the molar relationship for the 2 reactants. That's here. So I'm going to use this. 1 mole of TI to 2 moles F2. And we're almost there. I should have written. The problem tells us I have this much F2. What I'm calculating is how much I need. Finally get to the equal sign. All right, next, on the bottom, I'm going to have moles F2. So I'll be using this. So it's going to be 1 mole of F2 is 38 grams of F2 equals. At the end of this calculation is the amount of grams of F2 that I need to react with 2.4. 2.4 times 2 times 38 divided by 47.88. And to two significant figures, I've got 3.8.
That's what I got.
Okay, good. Thank you for checking. 3.8 grams. So what's our conclusion? We can make a conclusion now.
That fluorine's the limiting reactant. Or no, fluorine's not the limiting reactant because you have more than
This is how much we need. This is how much we have. So the conclusion is, you were doing it right.
Fluorine is limiting.
Fluorine is limited. If it helps you saying limited to get you there, well, that's just I guess limited is an adjective and limiting is a adjective. But we don't have enough. This is what we have, this is what we need, and we don't have enough. That makes this the limiting reactant. So that's our first step. We've discovered this. Necessarily, if that's limiting, that's excess. So as soon as we decide that's limited, we can go ahead and label that as excess. And I'll do this the other way too. I told you just pick one, and we just went with it. We chose TI to compare that to. But what if we had chosen F2? I just want to show you that you come to the same conclusion. If I said, oh, I'm going to do F2 first, and I went 1.6 grams of F2. Down here, F2, and it's these grams, so 38.00 mole of F2. And down here is mole of F2. That's the mole relationship, so 2 moles of F2. Have this, but we need 1.6 times 47.88 divided by 38 divided by 2. I know my hair looks crazy, but I'm starting to sweat in that thing, so gotta take it off. We need 1 gram of TI, but we have way more of it than we need, right? We need 1.0 grams, but we have 2.4 grams. So that's in excess, which necessarily makes that limiting. Same conclusion.
So we're trying to find like an excess to do both. Or you just start-
I'm just showing you, you come to the same conclusion regardless of which one you pick.
Okay.
So yeah, you didn't have to do that. This wasn't necessary. This is me just showing you that it all comes out the same. Sorry, were you still copying that down?
Yeah, it's okay. I can watch the video. No worries.
If I blinked this one out, then it wouldn't have messed you up. All right. That was B for 62. Stay with 62. And do C. This time they tell us 0.233 grams for TI. still gonna use that, and we're still gonna use these, well, at least one of them. No, we use both of them, yeah. I'll just go with the first one again. 0.233 grams TI. Grams of TI will be down here. This 47.88 grams is 1 mole of TI. Need to write a little bigger. This a little bit bigger. 0.233 grams of TI. Now we're using this. A mole of TI2. Two. And now 1 mole of 2. It's 38 grams. Of 2. Here's what we have. Here's what we need. Well, 233 times 2 times 38 divided by 47.88. This time it's 3 significant figures. And if I do it right, I get 0.370 grams. I did have to round to 3,698. All right, so that's what we need, and this is what we have. So what's the conclusion?
It was the same as the last.
It's the same as last time. This is how much I need, but I have less than that. So again, that's what I do. This problem, okay, for this one, I didn't do it for the last one I just saw, but all we did for the previous one was find the limiting reactant. What we need to do is actually calculate the yield now. We can double check those numbers. I feel like we're off for some reason. 0.233 and 0.288. Is that what I used? Yeah, okay. That's fine. Camera. Okay, but so far, all we've done is figure out limiting reactant. This is our limiting reactant in this case, just like last time. Okay, we calculated the limiting reactant. The next thing to do is calculate the theoretical yield. When you're finding limiting reactant, it's this molar ratio between the two reactants that you're using. Ti to F2. Molar relationship between the two reactants. You see that? That's what we use to find limiting versus excess. And we did that because we were comparing the two reactants for something. Now that we're going to predict the product, and it's the same theoretical yield of this, whereas limiting in excess refers to the reactants. The theoretical yield refers to the product. So, the reason we needed to know which one was the limiting reactant is because we're going to need the ratio of this product to the limiting reactant to be able to predict the amount of products. The excess reactant won't predict the amount of products. Only the limiting reactant will do that. So now we're using, now that we're here, now we're using 2F2 to 1 TiF4. 1 mole TiF4. So there's our limiting reactant, and there's our product. That's the relationship we need to predict the products. Well, we have to find the grams of the product, and we have to use the grams of the reactant to get there. So now we're going to go 288 grams of F2. Grams of F2 on the bottom. Now I'm going to use this. 1 mole of F2 has to be on the bottom. So moles of F2 has to be on the bottom. It's 2 moles of F2. 1 mole of TiF4. And now I need moles of TiF4 on the bottom. Is that right? 4 times 20 is 80, right? But that overestimates by 4, so subtract 4 from 80. Am I doing that right? Yes. Thank you. 8. Okay, 123.88. This is going to be our theoretical yield. Theoretical yield. Maybe I should put the whole thing. Okay, 1288 times 123.88 divided by 38 divided by 2. We need 3 significant figures. 0.469. That's our theoretical. So we found the limiting reactant, and then we went on and found the theoretical. This problem, if you look in the book, doesn't mention an actual yield, so there's nothing else to do here. The actual yield is, here's theoretically, if we very carefully measure this many grams of F2, and we very carefully measure this many grams of TI, we put them into react. Typically, we don't get all of this. We lose something somewhere along the way. It's typically a little bit lower than this. So what you actually get on the scale after this reaction is the actual. Theoretically, this is what you should get. In actuality, you usually get 99 point something of it, or 94 something percent of it. So let's go on to I did end up writing down odd ones. So let me go back here and write down the even ones. Y'all get the odd ones. Yeah, so I needed to do the even ones. It'll take a second to write these down. It's 65. No, y'all get the odd ones. I want to do the even. 64. Not 64.
Texas.
I suppose you could skip 68. It'll give you the reaction. All right, 64 though. There's the reaction. So we go in order again. Oh, this question says, here's how it's phrased. It says 13.1 grams of this and 13.6 grams of this are put into react, and later 12.4 grams of this is collected. It didn't call it the actual yield. You're just supposed to understand that that's the actual yield. because that is actually what was collected. We still have to calculate a theoretical yield, but because we've been given this, we can also calculate a recipient. So this is the actual yield. That's the actual yield. We'll use that in a little bit. 13.1 and 13.6, is that right? 13.1 reacts with 13.6, yep. Okay, so we're here trying to find the limiting reactant. What do we do first?
Pick one.
Pick one. Remember that. I'll give you a list. So if you wanted a list of steps, first thing you can do is find the limiting reactant. To do that, pick one of the reactants and then go through that walk to find out how much of the other reactant you need. I'm just going to pick Mg because it's first. You know, like here's how much I have of O2. 2Mg. 13.1 grams Mg, and I can just look on the periodic table. And Mg is 24.31. So that's the grams per mole for the Mg. Oxygen is 16, that means O2 is going to be 32. So we're going to need that too. All right, 2431. So grams of Mg, moles of Mg. So when you're finding the limiting reactant, we're going to use the grams per mole each. And molar if you want in words what I've been doing here. Molar relationship of the two reactants is where I am. This is the grams per mole of one of the reactants. I'm going to need the grams per mole of the other reactant before I'm done. So you need the grams per mole of each reactant and the molar relationship between the two reactants. That's what I'm using in this calculation. This is grams per mole for Mg. It's 2 moles of Mg to 1 mole of O2. It's this 2 and this 1. 2 moles of Mg, 1 mole of O2. Now we need moles of O2 on the bottom. I'm talking about this. Mole of that is 32.00 grams of O2. Here is what we need. $13.1 times 32 divided by 24.31 divided by 2. We're going to be in three significant figures, so I got 8.62 grams of O2. That's what we need. This is what we have. So what is O2? It's excess. We have way more than we need. So this is excess, which necessarily means this is limiting. So we have discovered which one is the limiting reactant. So you pick one and it's going to tell you which one is limiting and which one is excess. You don't have to do both reactants this way. If I did oxygen starting here and went across, we would find that oxygen is in excess, and we would find that Mg is limiting. Okay, from here, to find a limiting reactant, the next step now we're going to use that limiting reactant we've discovered to calculate the product of AKA predict the amount of product. Which is the same thing as saying to find the theoretical yield. We're also going to need the grams per mole of NGO, which is going to be 24.31 plus 16. So that's the grams per mole for MgO. There's one Mg, there's one O. Add them up, that's the grams per mole. Grams per mole of MgO. Between the limiting reactant and now we're using the molar ratio of this to this, because that's why we found the limiting reactant. So 2 moles of Mg to 2 that molar relationship specifically. So we'll start with limiting reactant, 13.1 grams. The grams per mole for Mg is 24.31. We're going to need moles of Mg down here. This is that molar ratio. 2 moles of Mg, 2 moles MgO. That puts moles of MgO down here. We're using this now. 40.31 grams. MgO. And this is that's the theoretical. Theoretical. Times 2 times 40.31 divided by 24.31 divided by 2. No, it hasn't done something wrong there. We'll try to do 13.1 times 2 times 40.31 divided by 24.31 divided by 2. Good. Yeah, I had 200 and something. Cool. Then we got 3 significant figures, and then it'll be there's our theoretical yield. All right. This is how much they say they actually collected. And the formula is sorry, am I racing too fast? I am. You guys want this back? I'm just trying to make some space.
Okay.
Anybody want this? You do? All right, let me put it back. Grams of G. That was 24. 31 grams of Mg. 31 grams of Mg. And this was the molar relationship of 2 moles of Mg, 2 moles of MgO. Can I erase this? That's where I'll do the percent yield. Percent yield is always actual over theoretical. Actual over theoretical. So I'm going to put the actual yield, 12.4. grams. You can put the MgO here. And down here is going to be the theoretical is 21.7 grams GO. percent. Equals. Notice that cancels and that cancels. As far as some kind of unit, it just come down to a percent. So it's 12.4 divided by 21.7 times 100. And that looks like it's near 90%. 12.4 divided by 21.7 100. Three significant figures. So this comes down to 57.1%. So again, it's finding the limiting reactant and finding the theoretical yield. It takes so long. The rest is pretty simple. Actual yield is usually just given. You just have to recognize it that it's an actual yield.
We don't have to go into that today. That stuff.
What's that?
There's stuff on the board. Combustion.
It would actually be exactly the same.
I see.
I was just going to go on and do 68. 68 is a twist because they don't actually give you the reaction. They say it in words. But let me do that one just as another exercise. And I might just stop there. SiO2, isonadhered, magnetic reaction with solid carbon. Yeah, I'll do this one more. Does it seem all dark? It seems darker than it should be. So this is number 68. It's an even one, but they didn't give you the reaction, so I'm going to give you Did you say that about combustion because you hate combustion?
Yeah, nothing.
I don't make out balance these. Combustion reactions are notorious for being a real big pain in the ass to.
I agree.
That's why you didn't want to do it, but I wouldn't have made you balance it anyway. I would give you the balance reaction,
thank you.
and then you would just continue the way you did it.
That's nice.
Because it doesn't teach you chemistry. All right, this is 68. the silicon dioxide plus 2 carbons. It's pure silicon, 2CO. They're telling us kilograms of SiO2. They're telling us for carbon, and then for the product silicon, they're saying 71.2 kilograms. Since the periodic table is in grams, aka grams per mole, let's just go ahead and turn these into grams, and then we'll move forward. This many kilograms is 1774 grams. This is 100. So I know these are huge numbers. There they are in grams. I've just moved the decimal 3 places to the right. So that's what I'm going to put here. The fact that they're huge numbers don't change the process at all. 177. The problem is describing an industrial process, and they always do things at a big scale. And then you produce, here's our product. Grams. And this is actually so here's our setup. That many grams of silicon dioxide, that many grams of carbon. And we're trying to calculate we're given an actual yield, so we can calculate a percent yield. So that's our goal, is the percent yield. The hard part is finding the limiting reactant to start with. I'm just going to start with SiO2. Is 12.1. So SiO2 is going to be plus 16 plus 16. One of our relationships. Carbon is just 12.01 grams of carbon is 1 mole of carbon. And silicon is just going to be 28.09 grams of silicon. We're going to end up using these 3 mole relationships. Why it's up.
The camera hates you today.
Huh?
The camera hates you today.
Is it my hair?
Maybe it just is grumpy that it's early.
Let's do it then. Well, I don't know what to do. Focus. How do I make it focus? It's supposed to autofocus. I suppose autofocus isn't working. Okay. Stay steady. You got it. You got it. Stay with us. And maybe. Oh, okay. Maybe. Let's stay with it. So that many grams of SiO2. We're going to use grams here. 60.09 grams of all. Mole. So we're using this molar relationship, which is 1 mole of this to 2 moles of carbon.